Okay, so now we're going to shift gears and we're going to talk about selection. Selection came in, but now we're going to talk about selection per se, and we're going to do this in two ways to look at selection. The first way we're going to look at today is just looking at the change in mean, the change in variance, the change in covariance that's induced by some mysterious forces of selection, characterizing selection just by changes in the first and second moments of phenotypic distributions. And this is sort of the old way of doing things. You look at the change in the mean, you look at the change in the variance, and you just standardize those measures. And then I guess it's my lecture tomorrow, there's another way. So I'm going to introduce some coefficients, beta, gamma, primarily, and we're just going to think of them as standardized ways of looking at how the mean and the variance changes within a generation due to selection. And then the first lecture tomorrow, we're going to go back and look at the same coefficients, but we're going to show that they are coefficients that describe a selection surface and also an adaptive landscape. And that's a sort of geometric way of looking at all of these primarily two kinds of coefficients, beta and gamma. Okay, and then after this lecture, we're going to turn to the evolution of the G matrix. That's going to be Adam's topic, and then we'll do an exercise in which we use Adam's G matrix simulator to actually simulate the evolution of the G matrix. Okay, but here we are. We're going to look at selection on single and on multiple traits, and I provided a picture of this is the blue-billed malimbe, a Central African bird. That's not me holding it. And this is to remind us that because this is a relatively straightforward operation of comparing phenotypic variances before and after selection, these measures of selection have been used in a lot of field studies, and so we know quite a lot about the distributions of these selection parameters that I'm going to talk about, or their estimates. And they prove useful. Okay, so again, I always do things in threes, right? 3, the magic number. Thesis in 3 parts. Just 3 main messages. Selection changes trait distributions, and we're talking about now within a generation. And so what we want to do, it turns out that what we want to do is contrast the distributions before and after selection, and we're going to show that this provides a powerful and sense of useful description of selection. Now, what you might think of doing, now, what else could you do? Well, you could compare the survivors with the non-survivors, and that's a much less useful comparison, although it's actually intuitive. It's more intuitive to some people. And then our third point is that multivariate measures of selection can correct for the correlations, the phenotypic correlations between traits. We talked about the problem of genetic correlations between traits in thinking about response to selection. There's also a problem of correlations, phenotypic correlations between traits in interpreting coefficients of selection. And some coefficients are easier to interpret than others, as we'll see. Okay, so here's our outline. What we're actually going to do in topics is we're going to look at how selection changes the univariate trait distribution. I'm just going to do show you some theoretical examples. We're going to introduce a couple of measures of selection. S, the linear selection differential, which is just the shift in the trait mean from before and after selection. C, the nonlinear selection differential, which is the change in the trait variance from before and after selection. And we're going to look at examples and surveys of those selection differentials. And then we're going to turn to the multivariate case, and we're going to look at how selection changes the multivariate trait distribution. And we're going to look at parallel measures of selection, the directional selection gradient beta, which is a vector, the nonlinear selection gradient gamma, which is a matrix, and then I'll show you some examples and estimates of what those look like. And then what we're going to do first thing tomorrow is go through the whole set of things and show how these also characterize selection functions and selection surfaces. We're going to put that off just so if we do it all at once, it tends to be a little bit overwhelming. This we can do pretty quickly here. All right. Okay, so here's a simple example. Let's suppose that we have truncation selection. I'm trying to remember how I did this. Let's see, what did I do? Here's obviously the truncation point. Yes, I do remember. So this is the sample after selection. So these are the individuals that die. And what we're saying is what we want to do, what proves to be most useful is to compare the distribution before selection with the distribution after selection. Now, the distribution after selection could be the survivors, right? As in this example. It's natural to think of these as the individuals that are beyond the truncation point. But this could also be, but what we really mean here in general are the individuals before selection weighted by their fitness to the next episode, okay? And in the case of survivors, there's a 1-0, sort of a 1-0 fitness difference, but we could weight the individuals by their fecundity, right? In which case we'd be characterizing fecundity selection, and we wouldn't have typically a truncation value. So this is just the first illustration is truncation selection, but we're talking about a more general approach. I'm going to take a minute here and introduce Landy notation. But we're talking about a very simple thing. So if you went back to the case, so let me just back up, and there's a sort of standard thing I do here in these figures that I need to point out. So what I'm going to do is standardize the variance of this distribution before selection so that it's 1. Right, and I do that by going through and dividing every trait value by the standard deviation in the original distribution. And then this distribution will have a standard deviation and a variance of 1. We'll show you that numerically. And then when you look at the distribution after, it's very easy to compare the variances. And I think I may have also standardized this so that we'll have to look at the next slide. I can't remember whether I standardized the mean as well. Yeah, so what happens here is this is the selection differential that we talked about before. Here's the mean after selection, which we're going to signify as Z bar star. And here's the mean before selection. It's very close to 1. I tried to do a standardization, was off slightly because I don't know, just the size of the sample. And so the shift in the mean is then 0.17. But because this is in units of phenotypic standard deviation, what we're saying is we've shifted the mean in that direction, in the upward direction, by 17% of 1 standard deviation. So that's the point of the standardization. And it's easy to remember the order in which you put these, because if you're shifting the trait in that direction, you want the larger value here, and you want to subtract the before mean here, so you get a positive value for S. You with me? If you flipped it around, you'd have a negative S when the mean is shifting that way. That's harder to think about. All right. Now, when was the last time you wrote an integral after taking calculus as an undergraduate? So I didn't particularly like calculus, but it turns out to read Landy's papers, you certainly have to integrate, and occasionally you have to take derivatives. And so I want to introduce you to this notation and demystify it so you don't freak out when you look at these papers, and and it's helpful to be able to read them. So let's look at these expressions. So let's just start with Landy's way for writing the mean of a trait. So now think about a sample of individuals, and you're going to take the mean, right? What you're going to do is you're going to take each of the trait values. One way of calculating the mean would be to take all of the trait values and order them, right? And then take all of the individuals with a trait value of, say, 1, and say, here's the proportion of individuals in the sample with that value. So you multiply that proportion times 1, and then you say, here's the proportion with a value of 2, multiply that by 2, and add it to the first. In other words, you weight the sample of individuals, weight the values for the trait by their proportion in the population. You with me? You could just add them all up, but this is a slightly faster way of doing it. And that second way of doing it is exactly what's going on here, right? Because look at what's inside the interval. You pick up a trait value, you multiply it by the probability that you observe that trait value in the population. That's what P of Z is. And then we're going to integrate over the whole distribution. So this is, if you think of this in sigma notation, here we're doing it for continuous distribution. This is just the standard formula for calculating a mean. True or false? Say yes, Steve. Yes, I recognize this. I am not freaked out. Okay, so now let's suppose that the trait distribution, which this is our thesis, is changed by selection. So now we have a new distribution, and we're going to call it P of Z star, right? And this is going to be the frequency of individuals after selection, and they have the same trait values. And so if we want to calculate the mean after selection, this is the expression. It's just a special case of our standard formula. We've just changed the frequency distribution. That's all selection did. Some individuals have dropped out, or they got new weights because they were especially fecund or whatever. And so this is a weighting that reflects their fitness. And in fact, here's our expression for P star of Z. It's each individual frequency. So this is the frequency of individuals, say, with a 150 body vertebrae. And here is the relative fitness of those individuals. What do we mean by relative fitness? We mean that average fitness has a value of 1. Standardized, so that's true. Okay? You're copying this down. That's good, because something happens when we write. It's good to take notes, isn't it? It burns it into some part of our cortex. All right. So here we turn to the rationale for taking the difference between the means of the population of the sample before selection and after selection. If we take that difference, we can show that that difference, S, is equivalent to the covariance between the relative fitness of individuals and trait values. And this is a little bit of algebra to show that's true. And I'm not going to go through it step by step. I'm going to skip a few steps, so I just want to give a flavor of what you do here. This result is due to Alan Robertson, in a paper in 1966. And it turns out to be a central result in some of the statistical equivalencies that we'll make later. First of all, let's just begin for continuous distributions, the standard expression for the covariance between two random variables x and y. All right? So you know, if you did this in sigma notation, that what you would take is all of the deviations in x from their mean and all of the deviations in y from their mean, take their product, and if you were doing this in sigma notation, you just take that column of products, multiply them and add them up, right? But what we're going to do here, equivalently, is weight each cross product by the frequency of individuals with value x and value y for each of the two variables. You with me? That's what P of x and y is. That might be, for example, the probability proportion of individuals in the population that have 150 body vertebrae and 197 tail vertebrae, right? And here with P, we're going in the integral, we're marching through all of the possible combinations of x and y and adding them up, and that is our familiar expression for a covariance, just in Landy-esque integral term. Now notice it's just a shorthand. There's no I equals, x equals, minus infinity to plus infinity. X equals minus infinity. No, what is that called, Matthew? The indices of integration or something like that. Limits of integration, yeah. Matthew knows how long it's been since I do calculus. All right. All right, so we can do a little bit of algebra with these integrals, and I'm not going to show the steps, but you can easily convince yourself that since these are constants, you can pull them out of the expression, and if you do that correctly, you'll end up with an expression like this, so that here's an integral minus the product, the bars went together, minus the product of x bar and y bar, the two means. True fact. And this form is often used in the literature, but you can readily derive it. Okay, so those are general expressions for the covariance, two equivalent expressions for the general covariance between variables x and y, and now we'll apply them to the case we're interested in, because our claim is that the covariance between relative fitness and trait values is going to equal the selection differential. And if you follow through these steps, here we're just taking this expression and applying it here. This is our special case of this expression, and with a few steps added. And what you can show is that this little integral is equal to, actually we presented it before, is equivalent to the mean after selection. Okay? So not such an easy thing to intuit. Maybe Alan Robertson did, but very easy to show that the contrast between means before and after selection, S is equivalent to this covariance. And that gives us a handle that makes it possible to interpret the other coefficients of selection we're going to look at. Okay, so much for the change, the univariate change in the change in the mean of a single character under selection. Now let's look at the change in the variance. Okay, so let's see, I have to think about this for a second. All right, so I'm going to introduce a new coefficient of selection, and it's parallel to the selection differential S, but we're going to call it the nonlinear selection differential. We're going to call it C, and it's the difference between the variance after selection and the variance before selection. But I'm going to add this peculiar term, S squared, where S is the selection differential we just talked about, the shift in the mean. And why would we do this? And the reason we're going to do this is that it turns out that when we work through this expression, C, is also equivalent to a covariance. And that's the justification for adding this correction term. Now I have a little animation here. And I know that Dave likes these. Don't you, Dave?
Absolutely.
Thank you. And I can never remember which. And this is the one I was playing for you. So if we standardize the trait distribution to a mean of 1, essentially a mean of 0, and a variance of 1 before selection, is it going to ever come up? Are you all doing this? Oh, you're not. Then we will get curves that look like this. Yeah. Okay, so what we're doing here is we're showing, it's a very simple animation. I'm showing in blue a distribution, a Gaussian distribution that has a standard deviation of 1. Here's the scale, mean of 0. And then I'm showing you what different values of P star look like. And because of our standardization, what we can say is, at this instant, there was a 6% increase in the trait variance. Here, a 2%. Here, there's a 3% loss in variance. Here, there's a 7% loss in variance. Okay? So the simple difference between P star and P is very easy to visualize when you're looking at a trait variance that's 1 before selection. And I showed you the ribbon up there. You can get to some other animations straight away without using them. Okay. Now, and part of the reason I'm showing you this is tomorrow we're going to look at the same animation, but I'm going to show you the selection functions that actually produce these changes in the variance. And you might try and imagine, as you fall asleep tonight, try and imagine what the animation of the selection surface was. And if I tell you that the distribution is Gaussian before and after selection, that also gives you an important clue about the shape of the selection functions we're going to be looking at tomorrow. You could also dream about that. All right, so here's the interesting thing. C, that thing I showed you with that correction term, is a covariance, and I'm not going to go through the algebraic steps, but if you come in and substitute, this is the squared deviation of the values of Z from their mean. That's what Z squiggle is. Here it is. We can show that C, but not the simple difference in P star minus P, is a covariance. Big deal, Steve. Well, that's a very handy thing. And you can ask what I'm trying to think if I did it here. Where I'm going to tell. I'm going to come back. I guess in the next lecture, I'm going to tell you about what that S squared. I have to show you selection surfaces before that's going to make sense. What is that? So that's a question for now that hangs before us. What was that S squared term, that squared selection differential that we added on to the difference between the trait variance after selection minus the trait variance before selection and converted it into a covariance? We'll talk about that. Okay, so here's an example, an actual example. Peter and Rosemary Grant and their students studied Geospiza fortis on Daphne major in the Galapagos Islands, and they had this distribution of beak depths in their finches in fortis before a drought. And then after the drought, there were only 90 survivors out of the original 751 birds. And when they looked at the distribution, they found that the beak depth had been shifted from by about 0.6 millimeters. That must be, yeah, it doesn't sound like very much, does it? But that was the shift, and they can show that that's statistically significant. So that's the selection. That's an example of a selection differential measured in nature. Now you could divide it by the standard deviation of this distribution before selection to make it comparable from study to study if you wanted. Yeah. So you want to go back?
When we were deciding on sampling before and after selection,
yeah.
I guess that's kind of clear, but
yes, this is a subtle thing before and after selection.
Yeah, is it before? Well, okay. So anyway, but like, does it make any difference if we are sampling? Let's say, for finches or for big things, for big bugs or plants, it doesn't really matter. But for small, but like for tiny bugs, where does it matter to sample after reproductive age to take into account? Maybe. Does it make sense to account for that, to sample after the age of reproduction?
It depends on what you're trying to do. But for sure you want to be within a generation. So, and what do we mean by a generation? We're thinking of a sample of zygotes recently formed, and we follow those zygotes until the production of the next generation of zygotes. And everything just before that second sample of zygotes is within the parental generation. Okay? So a lot of things can happen. And if we want, remember we had relative fitness back there? If we want to capture lifetime fitness as it affects the trait, then for each individual we would like a measure of lifetime fitness which would be number of progeny produced in that lifetime. That'd be the standard in a non-expanding, non-contracting population. More complicated if your population is growing or declining, but easiest to think of that way. Now, what happens in field studies is you go to Daphne Major, there's a big event. It's not lifetime fitness, but it was an ecologically interesting event. A single drought shifted the mean by the amount that I showed you. So I was talking to Peter Grant one time, and he said, now here's an interesting calculation. He said, look at the whole shift in beak depth across the entire radiation of Galapagos finches. How many, from the smallest to the largest, you could measure that in phenotypic standard deviations. How many shifts equivalent to S would you have to do that, make that entire shift? And the answer is about 20. So that tells you that one drought is, it's for over 100 years you're not going to go drought, and shift like that. But the point is, that one ecological event is an appreciable shift relative to the entire change in beak depth across the radiation. So anyway, so the point is, the measurement of S in terms of the duration of time is at your control as an investigator, and it needs to be adjusted and interpreted, in some sort of ecological framework. There's no exterior. Aside from the fact that if you want to do lifetime fitness, you should have a conventional measure of lifetime reproductive success. Okay, so just moving on. So a simple thing to do would be and you could standardize by converting all of the means before and after selection with before you take the difference, or you can do it afterwards. So the square root of p, that's the standard deviation in the trait measurement. So if you did this difference in the raw scale, then you could standardize afterwards, and you'd have a selection differential in units of phenotypic standard deviation before selection. You with me? And we can look at those distributions in a large sample. I think this is Endler's compilation of data from about 1984, something like that. And I flipped the sign, so I made it all of, some of them are negative, some of them are positive. I flipped the sign so they're all positive. And they're all in the standardized units. So you can see the most common result is for the mean to be selected by 1/20th of a standard deviation or less. So by and large, the means aren't shifting very. There's an occasional event in which here's the Grants event, right? Well, I don't know what that was in standardized use, but it's relatively rare for the trait to be shifted by selection within a generation by a full standard deviation, and no recorded instances in this sample of a shift as large as 2 standard deviations. So that's an interesting distribution. Maybe negative exponential, something like that, but with the mode very close to no shift. It's a little hard to say because the bins are pretty wide here. This is I have to give a name to this. This is a graphical convention. Here I've drawn, I've said, what does that distribution look like if we converted it to a blue blue distribution before selection that was Gaussian, and then shifted the distribution after selection and showed that in black, right? And so what I've done is I've taken the bin widths, so that first bin is shown as the dark band, whitest dark band that's almost hidden by the blue, and then here's this one, and the next width, and so forth and so on. The point is, the actual picture of how much selection is changing the mean of distribution is nothing like what you're seeing in the textbooks, right? If you draw this in your class, you're going to go, the distribution before selection is like this, and then after selection, like that. is this far over. Well, that value has never been observed in the empirical literature. The shifts in the mean induced by selection, and these are various kinds of studies, right? Some lifetime, some, Bumpus data and an ice storm. Most of the shifts are very, very slight, which is an interesting fact that we want to take account in this synthesis I'm working on with this book. All right. Now, if we do the same thing with our standardized measure of the shift in the variance with this correction term. So let me tell you what that is. Here we're correcting for, when just directional selection acting on the distribution will also contract the variance. And so that's apparently what's going on here. If we put that's the amount, if we put back in the amount that you expect variance to contract by directional selection, this is telling us how much contraction we got from stabilizing selection. And here we're just standardizing it by P, right? That's so now this is, it tells you immediately the fraction of variance contracted. And we get a more interesting distribution when we do that. So I should put a red line or something in here for the distribution for the 0 point. It would be right about there. And if you're in the front row. So what this says is, in all of these studies, variance contracted, but in all of these studies, variance expanded. So if you like, this proportion stabilizing selection and that proportion disruptive selection. You're nodding your head? I hate this. Because my world would be a lot nicer if this mode was over here and we'd hardly ever get expansion of variance. But this is, whatever this means, and I think it's subject to a variety of meanings, that's what we get. We'll get another picture when we go to the multivariate measure of variance contraction or expansion. Okay, so how am I doing for time? I'm getting expansive here. 12:15. How do I always do this, don't I? Okay, so I only had 15 minutes of discussion to begin with. Felipe and a few of you have asked questions, so I guess I'm going to try and argue that this is a combined lecture and discussion, but Joe should be frowning at me like this. All right, so I won't show the animation, so that'll speed us up. Okay, now we're going to do the same thing. I'll speed it up. Yeah, okay, yes. Questions are more important than listening to me drone on. You can always look at this, right?
I got confused with the previous slide.
Okay.
So on the
That one?
histogram,
Yeah. It's hard to see the scale down here. I think that's part of the problem. So this is standardized nonlinear selection differential, and here is a value for 0 right about there. I guess it's somewhere in here, right about, let's call that the 0 class, right? So all of the studies on this side, variance expanded, and on this side, variance contracted.
okay,
Does that help?
okay, yeah.
And then this is the same. So if you look at this, all of these studies up here are contractions in variance, and all of these studies over here, this is, so I mean, again, we're not talking about a huge change in variance before and after selection. And there's actually a preponderance of contractions, but there's quite a few studies in which the variance expands, although not hugely. So this is disruptive selection, but notice it isn't producing a bimodal distribution, right? Like we also like to draw in our textbooks, but I never draw in class because I know that that's not the empirical result at all. All right. Okay, so now we're going to go to the multivariate case, but we're just going to look at two traits. So here's an example trait. This is a phenotypic distribution, and it has the same drawing conventions as we use for the G matrix, right? Principal PC1, PC2, 95% confidence ellipse for the points. But these are individuals, not genetic values. Let's suppose that, and that the correlation, we standardized the variances before selection to 1, and so the correlation is same as the covariance, it's 0.9, and the mean is 0. And now I'm going to let some kind of selection act, and what the form of selection is such that all of the individuals colored in black are going to be the sample after selection. And if we calculate the variance and the mean of those individuals after selection, we see that the mean is shifted from 0 to 0.4, 40% of a standard deviation in both traits. And I think I show that as an arrow in the next slide. Is that the same one? Well, let's go here. So this is the selection differential, the directional selection differential in this case, and it's now a vector, right? And so we have two shifts, the shift in trait 1 and the shift in trait 2. And in this particular example, they are actually, do I show them? Yeah, they both got to be 0.4, right? Because they're 0 before selection. Okay, so familiar algebra just stacked into a column vector, which we'll need later. Speeding up a little bit so we don't go into our lunch hour. And now we're going to define this new thing. What happens, though, is, and what I'm going to show here, is that the selection differential can give us a misleading picture of what's actually going on. Let us define the selection gradient, the directional selection gradient beta. And we're going to do that thing we talked about before. We're going to collect terms this way in our Breeder's equation. We're going to multiply the inverse of the phenotypic variance covariance matrix by the vector of S, which has got a little in two-variant case stacked like that. And then we get this product. Now, what is this thing? Well, it turns out that this value, this is a covariance. S is a covariance. This is the partial correlation between relative fitness and trait values for trait 1, holding the values for trait 2 constant. And if you go back, if Matthew goes back tonight and looks up in his statistics books, this is the standard expression for a partial regression vector. So that's a nice result. And that is why it's important to make S a covariance, because when S is a covariance and this is a variance covariance matrix before selection, then these have that nice statistical meaning. It means that we can estimate beta by finding a statistical program that can calculate a partial regression. Now we have to have all of the traits included in the vector to do that, but it gives us an avenue of estimation immediately. But what I want to do is now take a minute and show you the ambiguity of S compared with beta, because we're going to claim that beta is the direct force of selection on the trait, and then that makes us wonder what S is. And we can see what's going on if we rearrange this equation. So what we're going to do is we're going to multiply both sides of the equation by p, right? If we multiply this side of the equation by p, we get, there it is there. And multiply this side of the equation by p, p times the inverse of p gives us what? Those of you who took linear algebra or did the tutorial, Katie, gives us 1. It does in the scalar case. What does it give us in the matrix case? Because those are two matrices, right? Like 1, but what is it? It's the identity matrix. It's a matrix that has 1s on the diagonal, but 0s elsewhere. And when you multiply a vector times the identity matrix, you get S again, right? So that means that this side of the equation becomes S. This side of the equation becomes PB. Okay, so this is going to tell us the composition of P. We multiply this out, that row times this column, that row times that column. And here we see the expression for for S1, it is the direct force of selection on character 1 acting through its variance, plus the indirect effect of selection on trait 2 acting through the phenotypic covariance between the two traits. This looks a lot like the genetic correlated response to selection, but now we're talking about the compound nature of S rather than the compound nature of response to selection. Similar algebra, but different point. Okay, and you can immediately see, with a little imagination, that if we had a lot of traits, we had a lot of terms like this. And the more traits we measure, and the more traits in which selection is acting in the form of these beta vectors, the more complicated is the interpretation of S, right? Because it could be the sum of a great many terms if selection is acting on many traits. So that means this covariance is a very ambiguous measure of selection. Here's the interpretation of the direct and indirect terms. Okay, I'm going to let you look at that later. I know I'm going a little fast, but I don't want to be here all afternoon. And so here's an example of how it actually does make a difference in nature. If you go back to the Grant study in the case we talked about, the drought hits the Fortis population on Daphne, and we were going to measure 1, 2, 3, 4 traits, probably all positively correlated, but we ignore that and we just measure the standardized shifts in the mean, right? 62% shift upward 62% of a standard deviation upward in the mean, 50% shift upward, 60% shift upward, 49% shift upward. But all of these are in the same direction, right? According to the selection differential. The picture we get just from S is that selection is uniformly favoring large birds, birds that weigh more, birds with longer beak, birds with deeper beaks, wider beaks. If we go through and correct for all of the effects of correlation, we get a very interesting result, and that is, yes, there's positive selection, especially on this trait and this trait, weight and beak width, but on this trait, selection is actually in the opposite direction when we look at the betas. And there's actually, and if you read the original article, see there's an ecological functional interpretation for why this is actually true, because of the properties of during the drought. You actually birds with narrower beaks were favored because they could twist the seeds on these seed pods or something like that. Anyway, the general point is you can be misled by S. S and beta are going to give you very different answers. All right, so here's a lot of algebra that we're going to go over very rapidly, but it's completely parallel to the algebra we did for the shifts in the mean. But if you stare at this, you see this is the general expression for a variance, because instead of square deviations from the mean, we've got a vector product, and then weighted by the frequency or probability of that trait value in the population. So that's a completely normal expression for a variance or a variance covariance matrix. And so here's P star, just the change, using the frequency distribution after selection. We have the matrix version of our correction for the effects of directional selection. And at the end of a little bit of algebra, we can show that not a surprise, C is a covariance matrix. And that means if we want to correct for the effects of correlations between the characters on the contractions and expansions and variance and covariances, we need to do a slightly more complicated thing. Instead of just correcting once, we need to pre and post multiply by the inverse of the variance covariance. This is our correction for character correlations using C, a covariance covariance matrix. And that yields us a set of values called gamma, a matrix of gamma values that are are coefficients for the direct effects of selection on the variances and the covariances of the traits, analogous to the nonlinear, these are the nonlinear selection gradients. They're analogous to the linear selection gradients, which describe direct effects on means. I'm speeding up here a little bit. But here I've circled if you look at the compositions of, this is similar to the rearrangements we did. We can look at the contributions of direct and indirect effects. And you can see that C is composed of both direct and then a lot of indirect terms. So as before, these corrections for the correlations, covariances between traits lead to a gamma, a less ambiguous measure of selection. Okay, here's a survey of standardized selection differentials, very similar to the negative exponential distribution of values estimated for S. And you can see I've standardized so everybody's going in the positive direction. I just changed the sign and all the negative. That's an interesting result we'll come back to. And here's our bottom line. For all of the algebra, there's 3 simple points. What we've shown is the change in trait distributions before and after selection within a generation can be used to derive useful measures of selection. And the 2 major things that we accomplish is we can use those measures to distinguish between the effects of directional and stabilizing selection. Actually, using means and variances to do that had been going on for at least since about 1890. But with these matrix formulations, we can also distinguish between the direct and indirect of selection that are mediated between the correlations between the traits. And we'll have to talk about this later, but this takes us not all the way always, but part of the way towards correcting for the complexities of correlations between traits. It helps us identify the actual targets of selection among our set of traits. And I probably left enough time for 1 or 2 questions, but this is too much algebra in this talk, I guess. How many people would like more algebra in this presentation? You would? I think I just identified my problem. You'd like more? All right. Yeah, you have a question.
Algebraic. In the slide for 7, the nonlinear selection gradient, gamma.
Back here?
Yeah, what's that T?
What's the
that
T?
a gamma, and I'm not seeing it well. 7.
Here?
Yeah. No. Transpose. Oh,
Transpose?
I forgot. Okay.
Oh, yeah. So this is a vector, a column vector.
Mm-hmm.
S transpose is the same thing as a row.
Okay.
And that product then gives you that matrix. So this is the correction for the effects of directional selection on the variance of trait 1, the variance of trait 2, and here's the correction for the effects of directional selection on the covariance.
Cool.
You're right, I buzzed past that.
It looked familiar, but I didn't know what it was anymore.
Let's see what's going on here. Well, boy, do I have good news. Guess what we're going to do now? It's time for lunch. Today it feels like I'm never going to get off of this. And your problem is even more severe because you have to listen to me for virtually the whole day. Yeah,
I'm
before
sorry,
we go,
one more question.
one more question.
What would you do if you have overlapping generations?
The quick answer to that is I don't know. Let me think about that over lunch. Amazingly, I don't know that that's even been dealt with in the literature. So in the longitudinal measure of fitness, what you would actually like to do is follow a cohort, right? So you would pick a cohort of individuals, and you would follow them through time, even through their entire lifespan, and you would measure fitness in that cohort, and then you'd measure traits on that cohort. And incidentally, the traits we're measuring should not change during the lifetime of the individual by growth or by learning or something like that. So you have to define age-specific traits or experience-specific traits. So anyway, you'd measure traits that don't change and for that cohort, and ignore the other individuals in the population that are overlapping with them, right? And I guess what you would do is if you could handle it, would be you would measure the selection coefficients separately in each cohort, and then figure out some way of combining them, I guess, weighting them or something. Does that make sense?
Yeah.
I don't know that anybody's done that.
But most traits change during development, right? So
Well, vertebral number doesn't. And so what I'm saying is what you can do is you can define new traits like weight as a 2-year-old on your second birthday, something like that. Yeah. You know, the person who might have done this is, if you look at Cluttenbrock's study with a lot of collaborators on the red deer on Room, whatever that island is, where they have a isolated population off the coast of Scotland, and they've studied that population for many generations, and they would all be overlapping. It would be interesting to see how they measured selection. They certainly have, but I haven't looked carefully but that would be one data set where somebody would have confronted this problem with enough data to make a good solution to exactly what you're pointing to.